Okay, so far in your notes that you've seen this writing here, and I just wanted to add some stuff to it. You saw what a rational function is. It's a function divided by another function. All right. What an asymptote is a line in which the graphs approach, but they never touch. And I'll show you a vertical or a picture representation here real shortly. And a vertical asymptote we read is whatever makes the denominator undefined, or whatever, or sorry, whatever makes the function undefined, which would mean whatever makes the denominator 0. And a horizontal asymptote is a horizontal line that your graph will never touch. So as x goes to infinity or negative infinity, so as x gets really big, or gets really small, approaches big infinity, really big infinity, and approaches negative infinity, which is a really small number. All right, but the graph will never touch. It might look like it touches on a graph, but it'll never touch there. All right. Let me give you a visual representation of what an asymptote is here real quickly. An asymptote, if I were to draw a dashed line like this, well, actually, let's use a graph that we know. The graph 1 over x. Okay, the graph 1 over x would look like this. And then on the other side, like that. We've all seen that graph before. And if you notice that this line right here, as it's going vertical, all right, this line, if you look on the graph, is going to get closer and closer and closer and closer and closer to this y-intercept, but it's never going to touch there. And the same thing going down here, it's going to come down here, and it's going to get closer and closer and closer to the y-axis, but it'll never touch her. That's an asymptote. And if you graph it with a graphing calculator, it'll look like the graph just all of a sudden jumps. It'll look like a goofy line, like in your graphing calculator. It'll look like this, and it makes a little jump like that and goes like that. This little area right here says it was actually, there's an asymptote there, but because we can of what we'll learn in this section, we'll know that there's an asymptote there without having to rely on that calculator. So there's also a thing called a horizontal asymptote, and actually in that graph that we already know, there's a horizontal asymptote. If you look closely at this graph as well, as x approaches, so as we're getting bigger and bigger number of values for x, so x equal to 5, x equal to 10, x equal to 100, x equal to 1,000, all right, our y values are getting really close to this x-axis, but it'll never touch it, all right? So that's what a horizontal asymptote is. It'd be right here, right along our x-axis, and our vertical asymptote is right here, right along our y-axis. All right. So that's what asymptotes are, giving you a visual representation of that real quick. But let me show you how to find it mathematically. It says determine the asymptotes of the graph of f of x equal to x divided by x plus 2. All right, so we already described how we find a vertical asymptote, and a vertical asymptote is whatever makes the denominator 0. All right, so if I were to, all we have to do is set the denominator equal to 0, x plus 2 equal to 0, and solve for x equals negative 2, right? In fact, if we chose negative 2 for this equation right here, negative 2 plus 2 is 0, and we all know we can't divide by 0. Therefore, we have a vertical asymptote at x equal to be negative 2. So we have a vertical line at x equal to negative 2, like that. And our graph will never touch that. Never touch that line. All right? And to find its horizontal asymptote, I'm going to go a different route than what the book goes. I'm going to actually show you or the calculus way we do it. For that, I need to quickly describe what a limit is. We're going to take a limit as x approaches infinity. So as x gets really big, so x is approaching infinity. We're going from 0, we're going from 0 all the way to 1 million and above. So as x is getting really big, a really big number, what we're doing is we're looking at what this graph is going to do, x plus 2. All right, I'm going to pause the video right here because I need to pull up a calculator, and I'll be right back. Okay, so I pulled up this calculator here to show you that as x is getting bigger, we're going to look at what number or what value that y is approaching. All right, it's approaching it, but it's never going to quite touch it. So let me plug in, I don't know, 10. 10 divided by 10 plus 2. All right, I get 0.8333, whatever. All right, so let's make a bigger number. So as x is approaching infinity, as x is getting bigger and bigger and bigger, let's pick 100. 100 divided by, so I'm using this, our function right here. I'm picking 100 for x. 100 divided by would be 102. All right, so 0.99999. All right, okay, so what if I pick 1,000 divided by 1,002? 0.99. Okay, what if I pick 10,000 and then divide by 10,002? All right, we're still at 0.99. Okay, I think you're getting the picture. What if I pick 1,000,000? 1, 2, 3, 4, 5, 6 divided by 1, 1, 2, 3, 4, 5, 2. Okay, I just plugged that into my x value. Again, we got 0.9999. Notice that it's getting very close to 1, but it's not ever going to get there. And you can always, if you're trying to figure out what a limit is, you can always go to your calculator and try to do this. All right, that's a little time consuming. I can show you a shortcut, however, though. And my shortcut is this. I'm going to take the limit as x approaches infinity, which means I'm going to divide, all right? I'm going to divide by the highest power of x, all right? So the highest power of x is x to the first power. So I'm going to divide every single thing by an x. Divide by an x. So x divided by x is 1. And then on the bottom again, x divided by x is 1 plus 2 all over x. And we already know that the limit is 1. We did that with our calculator, and we noticed that the values are getting really, really, really close to 1. And sometimes the values aren't that easy. So I'm going to show you this method that I'm doing here. So as x approaches infinity. After I divide by the highest power of x, all right, I'm going to plug infinity in for x. I'm going to plug infinity in for x. So there's no x here, so I have 1 all over 1 plus 2 all over infinity. Well, what's that mean? Infinity is not an actual number. We can't divide by infinity. So when your little brother or sister tells you that they're better than you times infinity plus 1, you can't do that. Infinity is not a number, all right? It's just saying it's more than you can count. But let's think of a really, really big number. If I take 2 divided by a really, really big number, like 10 billion, all right, it is very close to 0. And we say the limit of this function, 2 all over infinity, we say the limit of that is 0. So anytime you see 2 all over infinity or 5 over infinity or even 100 over infinity, all right, that's still 100 is a small number compared to infinity. That limit is 0. And we're just left over with 1 over 1. So we're left over with a asymptote at 1. And we found that. But I'm just showing you this method because it's not always that easy. All right, so we found our two asymptotes. We had a vertical asymptote at x equal to be -2, so we can put a line there, a dashed line there. And then we had a horizontal asymptote at y equal to be 1, like that, because we took the limit. All right? And then the remaining steps would be just if you were to graph this, you pick 2 or 3 values over here on the right side of this line to see where the graph's at. Maybe it's over doing something like that. And then you pick 2 or 3 values on the left side of the line, and maybe it's doing something like this and approaches those asymptotes as well. But right now we're just learning about asymptotes, and we'll graph those in a while. So B is kind of the same thing. It says determine the asymptote of the graph f of x equal to x divided by x minus 1. Well, we know that a horizontal asymptote is what makes the denominator equal to 0. So set it equal to 0. X minus 1 equals 0. X equals 1. We know that we have an asymptote at x equal to 1. And the same thing, and find our horizontal asymptote, take the limit. If x gets really, really big, of x divided by x minus 1. Remember, we divided by the highest power of x. In this case, it's x again. So x divided by x is 1. X divided by x for this guy is also 1 minus 1 over x. And again, remember, I plug infinity in for it. So anywhere I see an x, I'm going to plug in infinity, and I know that any number over infinity, that limit goes to 0. It just turns into 0. All right, and what's left over, I have 1 divided by 1, which is 1. So I have a horizontal asymptote in this one as well at y equal to 1. All right, those two equations were very similar. So that's why they both had a horizontal asymptote at 1. All right, that's not always going to be at y equal to be 1. Translations of asymptotes. We know that this graph, it has an asymptote at x equals 0 and y equals 0. It's the axes, or um, the x and y axis, right? It'll approach it, but it'll never touch it on our graph. Um, there are actually, they translate just like our graphs do. If we add one down here, well, we know that the horizontal asymptote then is going to move to the left one. It's just like graphing the function x plus 1 squared. We know that it moved the parent graph to the left one. Same thing with your asymptote. If it's down in the denominator, it's going to move your asymptote to the left one. All right. In the same case, if it's outside, it's going to move your horizontal one, up 3 actually. In this case, it's plus 3. All right. So we know that down here, our asymptote's going to move to the right 4. All right. That's my asymptote there, and it's going to go up 3 would be my horizontal asymptote. But I really wouldn't be too concerned about that. If you can do the limit thing that I showed you to find your horizontal asymptote, you will always understand where your horizontal asymptote is, because we'll take the limit as x approaches infinity of this, and you get 0, but our horizontal asymptote will always be at 3 in this case right here. Okay? And we'll get to slant asymptotes on a different page. I hope this helps.